We are trying to what? Represent the equivalent circuit simplified form like this using what? Thevenin's theory. In terms of that, you actually what? Convert the what? Line what? Magnetism part. Thevenin theory is made up of the RTH, resistive part. TH is Thevenin and XTH. How can we actually calculate for what? The voltage, the Thevenin voltage. Thevenin voltage is across magnetizing part. You consider the stator part together with what? The magnetizing part. So how can we calculate the voltage across this terminal? The voltage across this terminal is the same as the impedance here divided by what? The, this same impedance as the sum of what? Oh,
Hello, sir.
hello,
Yeah, good evening, sir.
good evening.
Please, if you can ask one of our colleagues to mute his microphone because we are getting feedback from his end.
Okay, then let me check and see. Okay, let me mute.
Yeah, I think it's Boama. It's Boama. Let's go on.
So I believe it's okay now. There are a whole lot of disturbances going on in my area. So the Thevenin voltage, the voltage, the impedance here, which was DXM, the impedance here, XM, DXM, over what? The sum of what? The impedance in the stator part together with what? The magnetizing part over R1, this R1, this R1, this R1, plus what? DX1XM, DX1XM times what? V phase. This is what? The voltage divided rho. If you want to calculate for the voltage across this terminal, use this equation. So that is the what? Same as for the Thevenin voltage. What about what? The Thevenin's line impedance. The sum of what? These impedances. You get it? As we can see, this and these are in series. They are in parallel this. So RTH and JXTH will be equal to what? R1 plus JX1. R1 plus JX1 parallel with what? DXM. That one is what? RTH. So the VTH can be reduced to this form. Yeah, actually what? This is the polar form. In terms of this, magnetic form, you do what? You VTH will be equal to what? The modulus of what? V phase times what? XM all over what? The square root of what? R R1 square plus X1 plus XM square. That is the magnitude. You get it? Magnitude. And VTH is further reduced to this. So this is the equivalent circuit of what? The formula for what? VTH. So keep this in mind. And RTH2 is directly proportional to this equation. The same thing applies to XTH. In terms of the XTH, it's approximately equal to what? X1. You get it? So this is the overall equivalent circuit of what? The induction machine. After using what? Thevenin's theory, you get the Thevenin's equivalent circuit of the induction machine to be in this form. So this is the what? Thevenin's representation of what? The induction machine. RTH times what? STH. You add the what? The rotor part. AX2 plus what? R2 IX2. So how can we calculate for I2? This is I2. I2 according to what? Kirchhoff's voltage law. VTH should be equal to what? The voltage drops across this side. So I2 will be equal to what? VTH from Ohm's law. The voltage all over what? The total impedance. All over what? The total impedance. So I2 will be equal to what? VTH over what? ZT. Is the same as what? VTH over RTH plus what? R2 over X, because they are the rare part. You get it? We are actually what? Interested in the modulus, the magnitude. That's why you want to get rid of what? The J. That's why you actually use what? The square root sign. You square them. The modulus. You get it? The denominator is the equivalent to what? Total what? Impedance. And the power converted to mechanical power, P converted to mechanical power, is given by this. The P converted is 3I squared. 3I squared, the mechanical power. Equivalent to what? Line impedance for the mechanical power is given by R2 into bracket 1 minus X all over X, as it was actually shown here previously. Resistance equivalent to what? Mechanical load. You get it? Because of the mechanical power, this part will be what? R2 into bracket 1 minus X all over S, the slip. So that the mechanical power will be what? 3I2 square. Because this one is just a phase. This is just a phase. So if you are considering the three phase, it will be 3I2 square. 3I2 square multiply what? Equivalent mechanical resistance. And also the torque induced will be equal to what? You don't know that power is what? Torque induced over what? Omega M. You get it? And the torque induced will be given by dAg over what? Omega S. Let's look at something. The torque induced. We are interested in this equation. Torque induced is finally given as what? 3 what? I2 square R2 by S all over what? Omega X. So we will actually use this equation to develop the torque induced torque in the induction machine. You get it? I2 is the same as this. So the torque induced, the general equation will be equal to what? 3 over what? Omega X. 3 over omega X. 3 over this omega X into what? I2. What is I2? I2 is the law of this part. This I2 square. I2 square multiplying what? R2 over what? The slip. Multiplying R2 over the what? The slip. What is what? The induced torque. It was deduced from this equation. Let's replace what? The I2 with this. So in generalized form, the square root sign to actually what? To be what? You want to get rid of what? The power, the 2. To be what? 3 will multiply VTH square. 3 to what? VTH square. And the square root sign, the square will get rid of what? The square root sign in the what? Denominator. You get this. So the torque induced formula, generalized torque induced in what? In induction machine using what? Thevenin's theory is this. So you need to keep note of this. Keep this formula in mind. Maximum torque. They are saying that maximum torque occurs when the power transfer to R2 by S is maximum. That actually takes place when R2 by X is equal to what? The line impedance. What equivalent impedance. This section. When R2 by what? X is equal to what? Square root of what? RTH plus XTH plus what? square root of what? RTH square plus XTH plus X2 all square. This is where maximum what? When this condition is already satisfied, maximum torque occur at this condition. Because of that, you can actually what? Calculate for the slip at its corresponding maximum torque. And it will be what? When you make the slip the subject, that means this one will come here and this one will go to what? Replace the denominator. You get it? And you get the what? ST mass to R2 all over this. ST mass will be this. So in terms of maximum torque, the slip is given by this relation R2 over what? This. So when you are actually asked to what? For maximum torque, the slip replaced by the slip in this S to be replaced by this relation. So after substitution, you get what? T max to be this. When you replace the what? ST max in this equation, you will get maximum torque to be this. Just take note of this what? Relation. In terms of what? In terms of what? Maximum torque, you just use this. In terms of torque induced, the generalized formula. T max given by this. The slip at maximum torque is directly proportional to the rotor resistance R2. The slip at maximum torque is directly proportional to what? R2. It is clear here from the formula. And so the maximum torque is independent of what? R2. This is the maximum torque. The formula for what? Maximum torque. As you can see, there is no R2 here. It doesn't include what? The R2. Therefore, the slip maximum torque is independent of what? The R2, the rotor resistance. Torque speed characteristics of what? The induction machine. This is how it looks like. It's induction motor. The torque speed characteristics. Induction motor.
Look at that.
The
Victoria,
what?
that's
Diagram.
Victoria, look at that.
This is for induction motor. And this is what? The generating part can what? Can act as a generator. Because the induction machine is the motor section. And this is the generating part. I just get rid of this. Just concentrate on this. Motor. Because you're not doing a generator. Induction generator. In terms of the induction machine can operate as a generator. How can we operate the induction machine as a generator? When the rotor speed, the rotor run faster than what? The synchronous internally generated magnetic flux. The induction machine will operate as what? Generator. You can just read this part. Speed characteristics using approximate circuit. Don't consider this. It's not necessary. It's the same as this one, the Thevenin's theory. Don't consider this section. Maximum torque. Most of the times we actually what? At starting. From here, look at this. This is the load torque. From here, full load torque is this. At starting, in terms of induction machine, it requires a very high what? Torque at starting. Starting torque is very high. It's most of the time twice what? Full load torque. The effect of what? The rotor resistance. Effect of what? The rotor resistance on the torque. And the rotor resistance is what? Actually increased. Actually increase the rotor resistance. The starting torque becomes higher. If you want higher starting torque because of induction machine, what you need to do is what? To increase the rotor resistance. As you can see from here, R1 less than R2. This is the starting torque. These are the torque and what? mechanical speed. Vertical section is what? Torque.
How
What?
did
The
you
mechanical
dispatch?
speed is the horizontal section, axis. Okay, so if you want a higher starting torque, what you need to do is what? Just to increase the rotor resistance. As we can see,
Maintenance
R6
dispatch public
is greater
car.
than R5 and
Oh,
what? R1. Where's R6?
Madam,
This is R6. As we can see, its starting torque is what? Higher
number
than
5
the
change
rest of
out.
them.
Built sidewalk cut.
Please, sir.
Hello?
Are we coming? Abogo.
Hello?
Oh my. Thank you. That's it.
So why induction motor has what? High starting current?
Hello, sir. Please.
Hello?
Some are at the back and they want to join.
Want to join? It will automatically admit them. Should
Sir,
admit
some
them.
want to join.
Cannot say, okay, they should try again. But I'm sure it will admit them automatically.
Come. Idabo. Yes, no, that's down. Just after my way now, yes. I'm a fire, my boy. Why?
Okay. Let's consider this example. So take note of this example. A 2-pole 50 Hz, no, this or you can just do it. A 2-pole 50 Hz induction motor supplies 15 kilowatts to a load at a speed of what? This. What is the motor slip? This is the speed. Motor speed is this. So all we need to calculate for is the what? Synchronous speed. And it's given by this. This is the motor slip. So that the slip is given by what? The synchronous speed minus what the motor speed by the what? The synchronous speed. Substitution. It to be this. This is the induced torque in the motor. The Newton meter under this condition. Induced torque. Instead of induced torque, the torque should be what? Related to what? The power. As you can see, they don't actually give us what? Any what? Forces. But we actually assume that P converted is the same as what? The P load. P load was given to what? The load, the power was given to what? 15 kilowatts. So P converted is the same as what? P load. So torque induced, we got what? The P load, which is the same as what? The P converted by what? Motor speed. Then let's do substitution. 15 kilowatt. 15 times what? 10 power 3. All over what? Motor speed. Motor speed was given to be this 2950. But this is in what? RPM. We just convert to what? Radians per second. I multiply it by what? 2 pi by 60 divided by 60. And this to be the operating speed of the motor. If its torque is what? Doubled. The torque is actually doubled. And just go through this. Let's consider this one. This one is not all that necessary. A 460 volts, 25 horsepower. See. 460 volts, 25 horsepower, 60 Hz, 4-pole, star connected ground rotor induction motor has the following what? Impedances. Ohm per phase referred to the stator circuit. So all these are the parameters. What is the maximum torque of this motor? At what speed and slip does it what? Okay. So what this, or let's use what? The Thevenin's equivalent circuit. Let's use what? The Thevenin's relation in terms of Thevenin's equivalent circuit. E max given by this. For we should be able to calculate for what? VTH, RTH, and what? XTH. You get it? We can calculate for VTH, RTH, and what? XTH. We can calculate for what? Maximum for this relation. For VTH, going to what? Thevenin's theorem. VTH given by this phi into what? XM all over what? Modulus of what? Impedance is what? R1 square plus S1 plus XM all square. Square root of them. So use this relation to calculate for what? The VTH. The V phase was given. And this is what? Line voltage. So you tell what? Convert it into what? Phase voltage. The star connected. For you divide 460 by what? Root 2.
What's the amount of 5 minutes?
Hello, sir. Can you hear me?
Yeah,
Sir?
I can hear you.
Yes, sir. You mentioned converting from RPM to seconds. So is it the NFE by the 60?
Yeah.
Is that
Pi
what
by
you
60.
mean by the conversion?
Bombay, are you coming? Bombay.
Something like
All
this.
right.
This is the rotor speed in what? RPM.
Okay.
So you convert it into what?
Yes.
Radians per second. In terms of the torque is in what?
Are you coming?
Omega M. Omega M is in radians per second. It's not in RPM.
Okay.
Yeah.
Okay.
So to be this is the what? This speed is in what?
So,
RPM.
so,
Just
please,
convert it into what? Radians per second.
is it because of the omega m that is why we are converting it into
Yeah, that's it.
seconds?
Because omega is measured in radians per second. Omega is measured in radians per second. The speed was given to be RPM. You get it? As the synchronous speed, NS, was given to be what?
Okay.
It was given in what? RPM. By omega.
RPM, yes.
Omega is in what? Radians per second. Therefore, you need to
Radians
convert
per
the
second.
RPM into what? Radians per second. How can we do that? Actually multiply the what? The speed, which was in RPM, by what? 2 pi by 60. This will be what? Radians per second.
Okay.
Bombay, copy, child.
So this is the VTH.
All right. So that's fine.
That's it, go.
Can we continue with how to find the RTH, ZTH, and what have you before we get to where you are now? Percy, your radio is giving us feedback.
It did this. VTH. This is the VTH from the equivalent circuit. The VTH is what? The general equivalent circuit of what? Induction machine. And according to Thevenin's law,
Okay.
we can convert it into what? Thevenin's equivalent circuit. You get it? How can we do that? We need to calculate for what? Thevenin's equivalent voltage. The Thevenin's equivalent voltage is the same as the voltage across the magnetizing component. That one is given by the impedance here all over the total impedance. Considering the stator part of the rotor. The impedance here is what? JXM all over R1 times what? JX1. No, R1 to be this. JXM all over R1 plus JX1 plus JXM. Add them together. The VTH according to what? The voltage divider rule. According to voltage divider rule, the voltage across this terminal will be equal to what? The impedance here is what? JXM all over the total impedance R1 plus J plus JX1 plus XM. You get it? Multiplying
Yes.
This multiply by what? The V phase. You get it? This what? The voltage divider
Yeah.
rule.
Okay.
You get the VTH. This how the VTH is actually calculated. So the VTH is in what? Polar
Okay.
form. We need what? The actual value. So we take the modulus of V phase. Do you get it? We want to get rid of what? The day. Do you get it? So to be XM all over the square root modulus or the real part. Do you get it? The real part. You don't want to
Yeah.
consider the what? You don't want to consider the imaginary part. So just use this complex numbers. This is the same as this. In terms of this, you get the real part. You don't get the imaginary part. You get the real part. So this is the formula for VTH. RTH is the what? Total impedance from here and here. R1, DX1, and DXM. As we can see, R1 and X1 are in series. So to be what? R1 plus JX1 or in parallel with what? XM. That will be what? That will be for the RTH, the JXTH. Thevenin's equivalent what? Resistance and line inductance. One is given by R1 plus JX1 parallel with what? JXM. Do you get it? This and these are in series. They are in parallel with this. That's what Thevenin's equivalent line impedance. So this is what the generalized equivalent circuit of what? The induction machine. This is what? The Thevenin's equivalent circuit of what? The induction machine. Made up of what? The RTH, the VTH will replace the what? The V
VTH.
phase. You get it? VTH will
Yeah.
replace the what?
Yeah.
V phase. We have what? RTH, the XTH, which will actually replace the stator R1 and X1, which are for the stator, the stator impedances. You get it? And we'll get rid of this part,
Yeah.
the magnetizing part. We see there's no magnetizing part here. Left with what? X2, X2, this is the X2, and what? The R2 by X, R2 by S. You get it? So from here,
Yeah.
the VTH can be reduced to this form, but I just forget about this part. The RTH, the same as R1. You get it? Into XM over X1 plus what? R1 into what? XM over X1 plus SM all square. This is the generalized formula for RTH. And the what? XTH is directly proportional to what? X1. You get it? When you have an X1, it's the same as what? XTH. RTH is calculated using what? This relation. You get it? The VTH, most of the time we do use this. I2, you calculate for what? I2. How can we calculate for I2 in this? According to what? Kirchhoff's voltage law or Ohm's law. You get it? The voltage drops in this, the same as what? VTH. V is what? IR. V is what? Let's say IZ. IZ. Z for the total impedance. So how can we calculate for what? I2. That means I2 be equal to what? Let me see. See something. Oh, I believe you understand what I'm saying. V is what? This is what? This is the total impedance. The total impedance. Let's say Z. Do you get it? V is what? IZ. How can we calculate for what? I will be equal to what? V over what? Z is the total impedance. Here be the case. These are the total impedance. You get it? So I will be equal to what? VTH over the total impedance. I2 will be equal to what? VTH. Because VTH should be equal to I2 RTH plus I2 AXTH plus what? They're all in series. You get it? And to be in this form, I to be equal to what? VTH by over what? ZT. VTH by ZT. The ZT is this, the rear part. You need only the rear part. You get it? This is the rear part. RTH plus what? R2 over S all square plus what? XTH plus X2 all square, because they are all in series. And you take the square root, complex numbers.
Mhm.
This is the general formula for what? I2. In terms of what? The Thevenin's equivalent circuit. Torque induced is I2. T converted is given by this. The torque induced equal to what? T converted, which is this, over what? Omega m. So the rule of this, you divide by omega m. You get this relation. Reduce torque induced. The general formula for the torque induced is given by this. 3 over what? It will be 3I2 square. What is I2? This is I2. The rule of this is I2. So you replace the I2 with this. So you'll be having what? 3 over what? Omega x. 3 over what? Omega x into what? I2. What is I2? The I2 is the same as this. Rule of this.
The network is breaking.
Network is breaking. So the whole of this is I2. 3I2 square over omega x. And you multiply by what? R2 over x. R2 over x. So this is the torque induced formula. And the reduced form, there is it. Maximum torque occurs when R2 over what? Xt mass is equal to this relation. Therefore, you actually what? Calculate for the slip. You calculate for what? The slip at maximum torque. You just make the slip the formula. That's S the formula. St mass the formula. Because maximum torque occurs when what? R2 over what? St max is equal to this. So by making St max the what? Formula, or making it stand alone, you get it to be this form. And they are saying that the slip at maximum torque is directly proportional to the rotor resistance. Slip directly proportional to what? The rotor resistance. The maximum torque is independent of what? R2. T max does not depend on R2. As you can see, there is nothing like R2 equation. Torque equation. But these are not relevant. This part, forget about this part. Using approximate circuits, the same as what the Thevenin circuits. Use that one, consider that one. Don't lend it. A 460 volt, 25 horsepower, 60 Hz, 4 pole, are connected one rotor, traction motor has the following impedances. Ohms per phase refers to what the stator what circuit. These are the parameters. What is the maximum torque? Maximum torque, that means you need to use what? The Thevenin's equivalent circuit, the relation for Thevenin's equivalent circuit. What is the maximum torque? It is maximum torque. Use Thevenin's equivalent circuit to calculate for what? The maximum torque. At what speed and slip does it what occur? So the maximum torque formula. This is the formula for what? Maximum torque. In terms of the torque induced, this is the formula for torque induced. Hello? Please, are you there?
Yeah, but
Yes, sir, we are there. The line is breaking small. That's why.
No, I'll record and I'll just send to you.
All right.
So before you can calculate for the maximum torque, we need to calculate for what? The VTH. This is a general formula. So you quote everything. Substitute. The voltage was what? 9 voltage. Get it? 3 phase. line voltage, but we need the V phase, and the star connected. The V phase is what 460, the line voltage over what root 3 times what XM. This is the XM. The XM was given to be 26.3 ohm all over R1 square 0.641 all square root of what R1 square plus what X1 plus XM. X1 plus XM. They are all given. Just substitution, and you get the VTH to be this. RTH, the general formula for what? RTH. This RTH is directly proportional to what? R1 into XM all over what? X1 plus XM all square. This is RTH. And the XTH is directly proportional to what? X1. XTH is the same as what? X1. So RTH, you use this formula. For what? RTH, you substitute and you get this. And the XTH is the same as what? X1. Yes, XT max, maximum torque. The maximum torque occurs when what? XT max is equal to what? R2 all over this. Do you get it? So for XT max, that will be what? 0.19. That's for XT max. That let's look at something. For the maximum torque. Maximum torque. This is the maximum torque. We just use this relation to calculate for what? The maximum torque. You get it? Let's do substitution. You know VTH. You have an RTH. You know XTH. X2 is provided. So you just substitute everything. The maximum torque. But look at something. The question: what is the what? Maximum torque of this motor? This part is not part. Right from here, calculating for what? VTH, RTH, and XTH. Use this relation to calculate for what? The maximum torque. They're saying that at what speed slip has it occur? That's why we calculate for what? The slip. Slip at maximum torque given by this relation. That is given by this relation. Let's do substitution. R2 you know everything. RTH you know. XTH you know. This is the slip. What about the motor speed? The speed will be what? 1 minus the slip. The slip is this. 1 minus what? 0.19 times what? The synchronous speed. The synchronous speed was given to be okay. You calculate for the synchronous speed. How many poles? This is 60 years. 4 pole. Okay, so 120 FE 120 times 50, 60 over what? 4. Calculate for what? Synchronous speed. You get 120 by 60 over 4 will be given by this. It's what? 1800 RPM. Get it? So the maximum torque, you just subtract what? Slip. The maximum slip from 1. 1 from what? You subtract the slip from 1 and you multiply by what? The synchronous speed to get the motor speed. 1 is done. What is the starting torque of this motor? Starting torque. At starting, the slip should be 1. This is the general formula. Where is it? Generalized formula for what? The torque induced. But look at something. At starting, slip is equal to what? At starting, the slip is equal to 1 because the motor speed is 0. At starting, the slip is equal to 1 because the slip is given by what? Synchronous speed minus motor speed or the synchronous speed. But at starting, motor speed is what? 0. Therefore, the slip is equal to 1. So at starting, we just replace x by 1. And the what? starting torque will be reduced to what? The relation for what starting torque will be the same as what 1 over omega x to what? Say VTH square times power 2. X is 1, you don't consider it. And this part 2 will be 1. Do you get it? The starting torque can be found from the torque equation by substituting what? You just substitute x to be what? 1. You get it? Because at starting, total speed is 0. Therefore, the slip what? 1. Do you get it? And you'll be left with this. So this is what? The starting torque. The general relation for what? A starting torque. So you do the necessary what? Substitution. You know everything. VTH, you know R2. RTH, you'll be able to calculate for it. You know all these things. XTH, you know them. So do your substitution and you get the starting torque to be this in Newton meter. If the rotor resistance is doubled, what is the speed at which the maximum torque now occurs? What is the new starting torque of the motor? If the rotor resistance is doubled, when you double the rotor resistance, then the slip at maximum torque also doubles. The slip at maximum torque also doubles. So the slip at maximum torque for the corresponding speed. Look at something. The slip at maximum torque is the slip at maximum torque. But when you double the rotor resistance, it will also double. So you multiply the slip at maximum torque by 2. And you get this. Get it. Corresponding motor speed will be equal to what? 1 minus what? The slip. When the rotor resistance is double. You get it. 1 minus this times the what? The motor the synchronous speed. It will be this. Maximum torque is still what? This. It will not affect the maximum torque. The starting torque is now. What is the new starting torque of the motor? New starting torque will be this. Combination of what? So I concentrating on what? This example. I working on it. Determination of what? Motor parameters. Due to the similarity between the induction motor equivalent circuit and what the transformer equivalent circuit, same tests are used to determine the values of the motor parameters. DC test. DC test actually determines what the theta resistance. Let's look at something. There is a DC test. The purpose of the what DC test is to determine what R1 theta resistance. A variable DC voltage source connected between two theta terminals. The theta terminals. You actually use a variable DC voltage source. Get it? So you actually vary what supply, the voltage supply, until what you are able to what measure rated current the motor, because the motor has its rated current, which is actually indicated on what the nameplate. There's an ammeter, and voltmeter. The ammeter and voltmeter will be connected. Keep on increasing the what the voltage, which is actually applied to the terminals, until what the rated current flows through what theta windings. Theta. DC source is adjusted to provide approximately rated theta what current. The resistance between the two theta leads coming from what the voltmeter and the ammeter. Because the reading from what the voltmeter will give you the voltage, and the reading from the ammeter will give you the current flowing through the theta windings. Therefore, when you are able to when you divide the voltage, the recorded voltage value by recorded uh, current value, that's what the theta resistance. RDC, you get RDC. The RDC will be what? VDC over what? IDC. R1 in terms of star, when the theta winding is what star connected, R1 will be equal to what? RDC. over 2. And it's what delta connected, it will be what 3 over 2 RDC. So this we calculate for what the stator resistance DC test. So DC test is actually used to what determine the stator resistance. No load test. No load test determines the rotational losses and magnetizing currents. The no load test determines the rotational losses and the magnetization current. So let's consider the no load test. The motor is allowed to spin freely. That means you don't connect any load to the rotor. It's allowed to spin freely. The only load on the motor is the friction and windage losses. The only load on the motor is only the friction and windage losses bearing. So all P converter, the P converter is actually consumed by the mechanical losses. The converted power is actually consumed by the mechanical losses, because there's no load connected. In normal power system, we all know that P in should be equal to P load plus the losses. But here being the case in terms of the motor, there's no load connected. Therefore, the P in will be equal to the P loss. Do you get it? The only load on the motor is the friction and windage losses. So all P converted is consumed by mechanical loss. The slip is very small. Slip is very small because there's no load connected. So the difference in speed between the synchronous speed and the motor speed will be very small. No load test. So this is the equivalent circuit of what? The general equivalent circuit of what? The induction machine. But let's look at something. This is mechanical part. This part actually constitutes for the mechanical losses. Let's look at something. At this small slip, because no load is actually connected to the rotor. Therefore, the slip will be very small. At this small slip, that means the impedance here will be very high. Therefore, R2 by 1 minus X over X, this impedance will be far greater than R2. At the same time, the impedance here, this impedance will be far greater than X2. That means these components are negligible.
Hello,
Yes.
sir.
Hello?
Sir, please. Someone want to join.
Someone want to join? Let's check.
Yeah, he want to join. He want you to accept him.
Okay, let's tell him to join. I'm waiting for him.
He's Galiba Kwaku.
Okay.
He's
Okay, couldn't join. Oh, you try again.
He has joined.
That's join, right? Okay.
Yes.
So because of this small slip, do you get it? Because of the no load, the slip will be very small, because the motor will be running at a faster rate, closer to the synchronous speed. Therefore, the difference in speed will be very small. Because of that, the impedance here will be far greater than R2 and RAX2. Therefore, we can just ignore these sections. So the equivalent circuit, this equivalent circuit will be reduced to this form. Do you get it? And this part, this section constitutes the friction and windage losses, because there is no load connected to it. Do you get it? And the losses, this part, the friction and windage losses correspond to this part, this section. We can combine the RC, the core loss. RC is the core loss component. AM is the magnetizing component. We can combine the core loss and that of the friction and windage losses together. So when you combine them together, they are in parallel. When you combine them together, you get this R friction and windage loss. And R friction and windage, together with the core loss, they are all greater than the XM. Okay. Well, let's look at something. At the no load condition, the input power measured by meters must equal to the losses in the motor. Do you get it? Because in terms of normal power generation, the P in should be equal to what the P load plus the losses. And since there is no load connected, that means the P in should be equal to what the losses. For at no load conditions, the input power, the measured input power, must equal what to the losses in the motor. The P rotor copper loss is negligible because R2 part is very small. The P rotor copper loss is what? Negligible because I2 is extremely what? Small. Because of this, let's look at something. This part is very large. That means it will offer a large impedance to current flow. Do you get it? For the I2 will be very small, more current will flow through the what? Magnetizing component and the core loss part. Because of the large impedance. Get it? The impedance is very large, more current will actually flow to that side, that section. They're saying that the PRCL is negligible because I2 is extremely what? Small. Because of this, the input power equals P in. The input power should be equal to what? The stator copper loss, the core loss component, and the what? Friction and windage loss. We not actually consider what? The rotor copper loss because I2 is very small. Therefore, it will reduce to 3I1 R1. This is what the stator copper loss plus P rotor. P rotor is equal to what? P core plus what? P friction and windage loss. Equivalence input what? Impedance is that input impedance is equal to what? V phase over what? Z I1. The input impedance. The input impedance is equal to what? V phase over what? I1. I1. V phase over I1 is what? The input impedance. If you want to calculate for the total impedance, do you get it? And that one corresponds to is approximately equal to what? The input impedance approximately equal to what? X1 plus Xm. Take note of this. X1 plus what? Xm. If X1 can be found in some other fraction, the magnetizing impedance, this is the magnetizing component, Xm, will be what? Known. The magnetizing impedance will be known. Therefore, the what? The no load test determines the rotational losses and magnetizing current. If you want to calculate for what? The magnetizing impedance, you can calculate for what? The magnetizing current. Another one, the locked rotor test. Locked rotor test or the blocked rotor test determines the rotor and stator impedance. Determines the rotor and what stator impedances. Similar to what short circuit transformers. So let's consider that one also. Blocked rotor test. This test, the rotor is blocked or locked so that it cannot move. Voltage is applied to the motor and the resulting voltage, current, and power are measured. In this test, the rotor is locked or blocked so that it cannot move. A voltage is applied to the resulting voltage, current, and power are measured. So we block the motor, we prevent it from what? Moving, and we apply what? Voltage. Wait, we measure what? The applied voltage, applied current, and what? The power. Do you get it? Okay, let's look at something. The AC voltage applied to the stator is adjusted so that the current flow is approximately full load value. AC voltage applied to the stator is adjusted so that the current flow is approximately the full load value. The lock rotor power factor can be found. It's very relevant. Let's calculate for the lock rotor power factor. And it's given by P over what? Root 3 VL IL. Because we all know that P equals what? 3 VL IL cos phi. But in terms of the log rotor, we will be able to what? Measure the P in, the power, the line voltage, and the line current. In this test, the rotor is locked or blocked so that it cannot move. A voltage is applied to the motor, and the resulting voltage, current, and power are measured. So with this, the measured power, voltage, and current, we can calculate what? The power factor. The log rotor power factor can be what? Found using this formula. Get it? The magnitude of the total impedance is also given by this. Magnitude of the total impedance is also given by this relation. Let's look at something. We have something like that what? LR, which is the magnitude of what? The total impedance, which is given by this. That is given by R LR plus what? JXLR prime. What is Z? Is the same as what? ZLR cos theta. The real part, RLR is equal to what? ZLR cos what? Theta. ZLR cos theta. The real part plus what? The JZLR sine what? Theta. So when you are able to calculate for ZLR, you can just calculate for what? RLR using this relation. RLR is the real part. It's equal to what? ZLR cos theta. And the JXLR is the imaginary part. So to correspond to what? Sine. RLR is equal to what? R1 plus what? R2. The RLR is equal to what? R1 plus R2. The R1 is actually measured, determined using what? The DC test. The DC test determines what? The stator resistance, R1. You get it? So with this one, we able to calculate for what? R1. When we know RLR, we can calculate for what? The rotor resistance, R2. And also X prime LR is equal to what? X1 plus what? X2 prime. X1 prime plus what? X2 prime. Where X1 prime and X2 prime are the stator and rotor reactances at the test frequency. At the test frequency. So that R2 is what? RLR minus R1. R2 just making the subject from here. For XLR, the actual XLR is given by what? The rated frequency over the test frequency times what? X prime LR. We need XLR, not X prime LR. When you are able to calculate for what? X prime LR, you can just calculate for what? XLR using this relation. Rated frequency over the test frequency. Rated frequency over the test frequency times what? X prime LR. Which is same as what? X1 plus what? X2. That's what? XLR. So there's a typical example. Saying that the following test data were taken on a 7.5 horsepower 4.08 volts 60 Hz connected induction machine having a rated current of what? 28 amps. The DC test, these are the values. VDC is given by what? 13.6 volts. IDC is also given by what? 8.0 amps. So from the DC test, we can
Please,
calculate what?
we can't see. We can't see.
You can see the screen
Yes, sir.
just now, or it happened just now.
Yeah, the screen does.
We can't
The
see
screen
the
doesn't
screen.
appear after
It
you.
doesn't appear.
Can you see it now? I believe you can see it now.
Yes, now, yes.
You see this part?
Yes, it's now okay.
You saw this section, right? During the explanation. I believe you saw this section.
No, sir.
So the following tests. Please see this section. I've just sent you the video so you can just see.
Hello, sir.
Hello?
Yes. Do we have this in our handout?
Yes, everything is in your handout. Everything is in it.
Okay.
After this,
All
I'm
right.
recording the
That's
video. I'll just share the video with you. Do you get it? You go to the video and you will get it. You get it. Following
okay.
test data
All
were
right.
taken on a 7.5 horsepower, 4 pole, 208 volt, 60 Hz star connected induction machine having a rated current of what this DC test. This is a DC test. Parameters: EDC 13.6 volts, IDC 28.0 amp. And from the DC test determines what the stator resistance R1. You get it? So you know VDC and IDC, you can calculate for what RDC is given by what VDC over what IDC. How can we calculate for what R1 when the stator is star connected? R1 is equal to what RDC over 2, and when it is delta connected, R1 is equal to what 3 over 2 times what RDC. For this, from the DC test, we know VDC, IDC. Therefore, we calculate for what RDC is given by what VDC over IDC, and VDC is given to be what 13.6 volt. The IDC for 28 amp. So we get this. The connection is what star connected. Rotor is stator is what star connected. Therefore, R1 should be equal to what RDC over 2. So now we look at what R1 to be what 0.243 ohm. You get it? Let's move on to the no load test. For the no load, given what VL, line voltage to be what 208 volts, frequency to be 60 Hz, the line current 8.17 amps, the P in to be what 420. No load test. Where is it? DC test. No load test. The motor is allowed to spin freely. The only load on the motor is the friction and windage losses. So all P converted is consumed by mechanical losses. The slip is what very small. Is what we did. In terms of the no load, P in should be equal to what the losses. P XCL plus P core plus P friction and what windage. So in terms of the no load, we calculate for the Z equivalent. Is what V phase for what I1, and I1 is also the same as what X1 plus what XM. X1 plus what XM. Okay. These are the parameters for the no load test. V1 and I1. That means you can calculate for what the Z equivalent. Calculate for this Z equivalent. The Z equivalent is the same as what X1 plus XM. No load test. Z equivalent should be equal to what the V phase as IA. What is the V phase? This was given, the line voltage was given to be what 208 volts. So you divide by what root 3 to get the phase voltage. So dividing by root 3, you get what 120 instead of 208. You get 120. Line current, that's of the what star connection. The line current is the same as what the phase current is what 8.17 amps. So you get what able to what calculate for the Z equivalent. The Z equivalent is the same as what X1 plus what XM is given by this. So you know X1 plus XM to be this. Lock load. The lock auto test.
Hello, sir. Question.
Yes.
Question.
Okay.
The Z equivalent, can't you use the simple Ohm's law by
Yes.
going by the V phase and then the I phase?
The V phase, you just use Ohm's law. It's the same as Ohm's law. Z equivalent is
Yes.
the same as Ohm's law. V V is what? V is equal to
Yes.
what? IR. So you make I the subject. Or V is equal to what? I times Z. You just make I the subject and to be equal to what? V over what? I.
Z. I. Yeah, so
Yes.
I'm asking, then you are saying you use the X plus XM. And
No, no,
I'm
no, no.
saying that, okay.
This is what? In terms of what? No load test. The Z
Okay,
equivalent.
okay.
X1 plus what? XM. They didn't consider what? You don't
Okay.
consider the what? The resistive part.
Oh, okay.
Total
Okay.
impedance. In terms of what? No load test. No load. So you don't consider the what? Resistance. So that no load. We're saying
Okay.
that this part. That is it.
Okay.
So this one, don't consider the resistive part. Consider only this part. The Z equivalent. Tell me the no
Okay.
load. You get it?
Okay. All right, sir.
So this is the Z equivalent in terms of the no load. And it's the same as what? It's approximately. That's why they are saying they're using the approximation sign. It's not directly equal to. It's approximately equal to what? X1 plus what? XM. So we get X1 plus XM, which is the same as what? The Z equivalent to be what? 14.72. Let's look at the lock roto. The lock roto test, VL, was given to be 25 volts. The line current was given to be 27.9 amps. Frequency was given to be 15 hertz. P in was given to be what? 920 ohm. Therefore, you can calculate for what? The power factor, the cos phi. In terms of the block rotor test, in this test, the rotor is locked or blocked so that it cannot move. A voltage is applied to what? Motor. The resulting voltage, current, and power are measured. With the current, voltage, and power being measured, and you just calculate for the power factor. When you're able to calculate for the power factor in this relationship, you also calculate for what? ZLR. And the ZLR Z lock rotor is also given by what? The V phase by I. Z lock rotor is the same as what? R lock rotor plus JX time lock rotor. Is the same as what? Z lock rotor cos phi. R lock rotor is equal to what? R lock rotor, the rear part, is equivalent to what? Z lock rotor cos phi. And the JX prime lock rotor is equivalent to this, the sine, the imaginary part. R lock rotor is equal to what? R1 plus what? R2. And X prime lock rotor is the same as what? X1 prime plus what? X2 prime. You get it? Let's calculate what? XLR. We need XLR, not XLR. We don't need X prime LR. Do you get it? Just use this relation, the rated frequency, the test frequency, by what? X prime LR to calculate for what? XLR. And the XLR is equal to what? X1 plus what? X2. So this, the lock rotor, given the line current, line voltage, which is what? 25 volts. Frequency to what? 15 hertz. Frequency, this is the test frequency. 15 hertz. This was the test frequency. This is the rated frequency. F rated is what? 60 hertz. You get it? F rated is what? 60 hertz. The test frequency is what? 15 hertz. So in terms of the lock rotor, line voltage was given to what? 25 volts. The V phase is line. You need the phase voltage and to be what? 14.4. The phase voltage is the same as what? The line voltage over root 3 at what? 50 hertz. The test frequency. Therefore, you calculate for what? Z prime LR. And Z prime LR in terms of the lock rotor test.
Trade 1, 2, 3, 4. I'm sure.
By what? I. Let me see.
Wow. Maybe our password.
It's the same as this. V phase over I. The V phase is 14.4 over the I, which was what? 27.9.
I'm going to say a bit mine.
And this is the same as what? R,
I'm
the modulus of what? RLR plus DX MLR. Calculate for what? The phi. Cos
Also,
phi.
Wi-Fi no connect.
Cos phi is equal to what?
Really plenty.
This is cos phi. Cos phi is equal to what? P in over square root of what? Root 3 over square root of 3 VLIL. I need
yeah.
phi, power factor angle. The phi will be equal to what? Cos inverse of what? P in over root 3
Hold on.
VLIL.
Okay.
So just use this relation to calculate for what? The phi LR, the power factor angle for the lock road test. So the cos phi, after doing the required substitution, we get PLR. PLR was given to be 920 watts. 920 watts root 3 VL. VL was given to be 25 volts and IL was given to be 27.9. That is what? IL. You get the angle to be this. Now RLR. We know the ZLR to be this. RLR. We know the what? ZLR. So RLR is equal to what? ZLR cos phi. ZLR cos phi. So RLR is equal to what? ZLR cos phi. You get it? This is the ZLR. It was given to be 0.516. So 0.516 cos phi. This is the phi. You get it? The angle cos phi. Get the RLR to be 0.39. Bear in mind that RLR, which is this, RLR is equal to what? R1 plus what? R2. Do you get it? R1 plus R2 is equal to what? 0.39. We were able to calculate for what? R1 from the DC test. DC test calculated for the R1 to be what? RDC over what? It was given as what? 0.43. So we know R1 already. We now know the what? RLR. So do the necessary substitution by making what? R2 the subject, and you get what? R2 to be what? 0.143. Let's move on to what? X prime LR. X prime LR, which is the imaginary part, it will be equal to what? The ZLR. The ZLR. The ZLR, which was given to be 0.516 sine theta LR. Sine theta. The theta was given to be 40.3 what? 6. There's a theta. Sine theta. And you get what? The X prime LR to be this. But the estimated frequency was this. The test frequency was 15. Therefore, you actually what? Calculate for what? The XLR. The XLR. The XLR using this relation. F rated frequency over the test frequency times X prime LR. So when you know X prime LR, the rated frequency and the test frequency, you can calculate for what? The XLR. So XLR is equal to what? F rated over F test times X prime LR is equal to what? 60. Frequency was 60 Hz. 60 Hz. And the test frequency was 15 Hz in terms of the lock root 2. 60 over 15 times X prime LR. X prime LR was given to be 0.335. And you get this value. Now you know that X1, if X1 is equal to what? X2. If X1 is equal to what? X2, that means XLR, which is the same as what? X1 plus what? X2. XLR is equal to what? X1 plus what? X2. So you consider X1 and X2 to be what? The same. So if X1 is equal to what? X2, that means XLR 2XLR equal to this, or 2x1. No, it shouldn't be 2XLR. Look at something. We know that XLR is equal to what? X1 plus what? X2. Now X1 and X2 are the same. Therefore, XLR can be equal to what? X1 plus X1, making what? 2x1. Or X2 plus what? X2, making what? 2x2. Therefore, XLR is equal to what? 2x1. So if you want x1, you divide what? The XLR by 2, and you will get what? 0.67, which is the same as what? X1, and also the same as what? X2. But let's look at something. X1 plus what? Z equivalent. X1 plus what? XM. So we know X1. We know the Z equivalent. Therefore, you can calculate for what? From no load test, we can calculate for what? The XM. Therefore, the XM will equal to what? 14.72 from the Z equivalent. 14.72 minus what? The X1 is what? 0.67. To be equal to what? The XM will be equal to what? 14.05. So these are what? The parameters of the induction machine. From the test, we've been able to calculate to determine all the what parameters of the induction machine. So after determining your parameters, you can now draw your equivalent circuit. Such the perfect equivalent circuit of this motor. So we are done for this slide. And also, let me see something. So we are done for the induction machine. There's a starting. Three-phase induction motor. So this one will be as a reading assignment. You can just read this. Direct online starter, resistance starter, transformer starter. Other types of what starters. So you should know this. Variable frequency starting. Direct online.